Welcome to the DX Today podcast, your daily deep dive into the AI ecosystem. I'm Chris, and joining me as always is Laura.
Hey, Chris. Okay, I am genuinely fired up about today's topic because it touches on something that I think is the elephant in the room for this entire industry.
And that elephant is electricity. Specifically, the insane amount of power that AI systems consume. But today we're talking about a research breakthrough that could fundamentally change the equation. Researchers at Tufts University have developed a neuro-symbolic AI approach that cuts energy consumption by up to 100 times while actually improving performance.
100 times. And that's not a typo, not a rounding error. Their system used just 1% of the training energy and 5% of the execution energy compared to conventional approaches. Those numbers are staggering when you think about the scale of the problem we're dealing with.
Let's set the stage here for anyone who hasn't been following the energy side of the AI story. How bad is the energy problem right now in 2026?
Oh, it's bad, really bad. The International Energy Agency projects that global data center electricity consumption will hit 1,100 terawatt hours this year. To put that in perspective, that's equivalent to Japan's entire national electricity consumption. The whole country of 125 million people, just for data centers.
And a huge chunk of that is AI workloads specifically, right?
Exactly. The Uptime Institute estimates that AI-specific data center power load will hit 10 gigawatts by the end of this year. And here's the kicker. That number is actually constrained not by demand, but by the fact that the power grid literally cannot deliver more capacity fast enough. The demand is there, the electrons aren't.
So we have a situation where AI companies are basically in a bidding war for electricity, and the grid is the bottleneck.
Right, and it's already hitting consumers in their wallets. Goldman Sachs put out analysis showing that data center-driven electricity demand will boost core inflation by 0.1% in both 2026 and 2027. Retail electricity prices have jumped 42% since 2019, outpacing the overall consumer price index. People are paying more for power at home partly because AI is gobbling up so much of the grid.
That's the kind of thing that turns public opinion against AI real fast. When your electricity bill goes up because some company needs to run another training run, people notice, and they get angry.
Absolutely. And Gartner is predicting that power shortages will operationally constrain 40% of AI data centers by 2027. 40%. That means almost half of all AI infrastructure could be limited not by chips or algorithms, but by access to basic electrical power. PJM, which operates the largest power grid in North America, is projecting a 6 gigawatt shortfall by 2027. That's equivalent to 6 large nuclear power plants just missing from the grid.
Okay, so that's the crisis. Now, enter Matthias Scheutz and his team at Tufts. Tell me about this neuro-symbolic approach they've developed.
So Scheutz is the Carroll Family Applied Technology professor in Tufts School of Engineering, and his lab focuses on human-robot interaction. What they've developed is a hybrid system that combines traditional neural networks with symbolic reasoning. And the key insight is actually beautifully simple.
Break it down for me. What do you mean by symbolic reasoning layered on top of neural networks?
Okay, so think about how you solve a complex problem. You don't just throw pattern matching at it, right? You break it into steps. You categorize things. You apply logical rules. That's symbolic reasoning, the kind of structured, step-by-step thinking that classical AI was built on decades ago, back in the 50s and 60s. What Scheutz's team did is combine that with the pattern recognition strengths of modern neural networks.
So instead of having a massive neural network brute force its way through every problem, you have a leaner system that actually reasons through the steps logically?
Exactly. And the results are remarkable. They specifically work with visual language action models, or VLAs. These are the models that let robots process what they see through cameras, understand language instructions, and then physically execute tasks in the real world. They're incredibly important for the future of robotics and physical AI.
These are the models that companies like Google and OpenAI are pouring billions into for robotics applications, right?
Yes, and they're incredibly energy hungry because they have to process visual data, language, and motor actions all at once. But the neuro-symbolic version that Scheutz's team built, it trained in 34 minutes. The conventional VLA model, over 36 hours. We're talking about a factor of roughly 60 times faster just for the training phase alone.
34 minutes versus 36 hours. That's not an incremental improvement. That's a completely different category of efficiency.
And the energy numbers back it up. Training the Neuro-Symbolic model required just 1% of the energy of the standard VLA system. During actual operation, when the robot is out there performing tasks, it used only 5% of the energy. That's where the 100 times less energy claim comes from, and it's well supported by their experimental data.
Now here's where I'd normally be skeptical. Usually when something uses way less energy, you're giving up performance. There's always a trade-off in computing. But that's not what happened here.
Not at all. And this is the part that really makes this research stand out from the crowd. They tested the system on the Tower of Hanoi puzzle, which is a classic problem-solving benchmark that requires careful sequential planning. You have to move disks between pegs following specific rules. The Neuro-Symbolic system achieved a 95% success rate.
And the conventional system?
34%. Not even close. But wait, it gets even better. They then tested on a more complex variant of the puzzle that neither system had seen during training. This is the generalization test. Can you handle something truly novel? The Neuro-Symbolic model still hit 78% success.
And the standard VLA on that harder test?
0%. Literally zero. It couldn't solve a single instance of the harder puzzle. The Neuro-Symbolic system wasn't just more efficient, it was dramatically better at generalization, at handling novel situations it hadn't been explicitly trained on.
That generalization piece is huge. That's basically the holy grail for robotics and real-world AI deployment. You can never train a system on every possible scenario it might encounter.
Exactly. And that's where the symbolic reasoning component really shines. Because it's not just memorizing patterns, it's actually learning logical rules and structures that transfer to new situations. It's the difference between a student who memorizes answers for a test and one who understands the underlying principles well enough to solve problems they've never seen before.
So let me play devil's advocate here. The Tower of Hanoi is a well-structured, deterministic puzzle with clear rules. The real world is messy and unpredictable. Can this approach scale to the kinds of complex, noisy environments that robots actually need to operate in?
That's absolutely the right question to ask, and it's one Schweitz's team openly acknowledges. They're presenting this work at the International Conference of Robotics and Automation in Vienna this June, and I expect a lot of the discussion will focus on exactly that scalability question. But there are several reasons for optimism.
Such as?
Well, symbolic reasoning has always been good at structured, rule-based domains. The historical challenge was combining it with the flexibility and perceptual capabilities of neural networks without losing the strengths of either. What this research demonstrates is that the combination doesn't just work. It works dramatically better than either approach alone. The question now is how far you can push it into messier, more ambiguous domains.
And from an industry perspective, even if this only works for certain categories of tasks, the energy savings alone could be transformative at scale.
Oh, absolutely. Schweitz himself made a really compelling point that puts this in everyday terms. He noted that the AI summary that Google puts at the top of search results consumes up to 100 times more energy than generating all the website listings below it. Just that one little AI-generated paragraph at the top of your search is using orders of magnitude more power than the rest of the entire page.
That's a perfect illustration of why this matters. Every little AI feature multiplied across billions of users and billions of queries per day adds up to enormous energy demand.
Right? And if you could apply neuro-symbolic principles to even a fraction of those workloads, even 20 or 30% of AI tasks, the aggregate energy savings would be enormous. We're talking about potentially freeing up gigawatts of power capacity that could go toward other uses or simply reduce the strain on an already overtaxed grid.
Which gets back to that grid bottleneck we talked about earlier. If you can make AI dramatically more efficient, you don't just save money on electricity bills. You potentially unlock more AI capacity without needing to build new power plants or wait years for grid interconnection.
Exactly. It's a multiplier effect. More efficient AI means you can do more with the existing infrastructure, which means faster deployment, lower costs, less environmental impact, and fewer angry ratepayers. It's genuinely a win across every dimension.
Now I'm curious about the broader landscape. Are other research groups working on similar neurosymbolic approaches, or is Tufts an outlier here?
There's actually a growing movement in this direction, which makes the Tufts results even more significant as a proof point. MIT has been doing significant work on hybrid AI systems. Stanford has programs exploring symbolic reasoning integration. And there is increasing interest from industry too. Companies are starting to realize that the brute force scaling approach hits practical walls when you're constrained by power availability and cost.
The scaling laws conversation has shifted dramatically this year. It used to be all about more parameters, more compute. Bigger is always better. Now there's a real recognition that efficiency and architectural cleverness matter as much as raw scale.
And this Tufts research really crystallizes why that shift is happening. When you can get better results with literally 1% of the energy, it forces a fundamental rethinking of the entire approach. Maybe we don't need trillion parameter models for every task. Maybe the smarter path forward is designing systems that think more carefully and more logically with less computational overhead.
Do you think the big labs, Google, OpenAI, Anthropic, Meta, are going to pivot toward incorporating neuro-symbolic approaches into their systems?
I think we'll see hybrid approaches become much more common over the next couple of years. The pure scaling play isn't going away entirely because some tasks genuinely benefit from enormous models with massive parameter counts. But I expect we'll see a new generation of systems that are more architecturally sophisticated, using the right computational tool for each subtask rather than throwing a giant neural network at everything.
It reminds me of the shift in software engineering from monolithic applications to microservices. Instead of one massive system doing everything, you have specialized components working together efficiently.
That's a great analogy. And just like the microservices revolution, it introduces new challenges around orchestration and integration. But the efficiency gains can be truly enormous if you get the architecture right. And the environmental and economic incentives to get it right have never been stronger.
What's the realistic timeline here? When might we see neuro-symbolic approaches showing up in production AI systems that people actually use?
For robotics specifically, I think we could see commercial implementations within 18 to 24 months. The Tufts results are compelling enough that robotics companies are definitely paying attention, and the energy savings alone make a strong business case. For broader AI applications like language models and search, it's probably a longer timeline, maybe 3 to 5 years before we see significant integration at scale.
But the energy crisis isn't waiting 3 to 5 years. The grid constraints are here right now.
No, it isn't waiting. And that's why this research is so timely and so important. Even if full neuro-symbolic integration takes years to mature, the underlying principles, using structured reasoning to reduce computational overhead, can be applied incrementally starting now. Every percentage point of efficiency improvement matters enormously when you're operating at the scale of 1,100 terawatt hours of global data center consumption.
One last thought. There's something poetic about the solution to AI's energy crisis, potentially coming from academic research at a university like Tufts, rather than from the giant tech companies with their tens of billions of dollars in R&D budgets.
It really is. Matthias Scheutz and his team are showing that fundamental rethinking of how AI systems work can achieve what brute force scaling simply cannot. Sometimes the biggest breakthroughs come not from building bigger hammers, but from realizing you don't need a hammer at all. You need a scalpel.
Well said. And for our listeners, we'll be watching the Vienna Robotics Conference in June very closely for more details on this work and the response from the broader research community.
It's going to be a fascinating few months. If this approach scales the way the early results suggest, we could be looking at a genuine paradigm shift in how AI systems are designed, built, and powered. The era of efficiency-first AI might be just getting started.
That's all for today's episode of the DX Today podcast. Thanks for listening, and we'll see you next time.